Blinking.
Are you ready with the jokes?
Yeah.
Okay, so today's lesson is on water hardness. So what we're going to do is we're going to be talking about hardness as a concept of water. The two types of water that we're dividing the solutions we have as water that's available for us to eat and drink with are hard water and soft water. But we're interested in hard water. Soft water is the default position. It means water doesn't have a lot of dissolved minerals. Hard water means that we have dissolved minerals, and in particular, the dissolved minerals that are important in hard water are calcium, present as a 2+ ion, and magnesium, present as a 2+ ion. These are reactive metals, so they're only ever found native, in other words, in the environment as a 2+ ion. Yes, in the back.
What are you talking about?
Don't make this any harder than it has to be.
That blends.
Another mineral that sometimes contribute to water hardness is iron. But in this course, we're going to concentrate on calcium and magnesium. And in many cases, we know that calcium and magnesium are in the water because of the environment we are in. What releases calcium and magnesium into the water? You there in the back?
Is it igneous rock?
Close. Not igneous rock, but it is rock. Do we have another answer?
Sedimentary rock.
You there in the middle? Sedimentary rock is correct. What is one of the main forms of sedimentary rock that is in fact made of calcium? Calcium carbonate, usually.
Is it limestone, Mr. Lemon?
Right over there. It's limestone.
Oh,
So
for
limestone
me.
contains these minerals. Calcium carbonate is a big component of limestone because it's made from the crushed shells of long-dead marine organisms. And if water sits or passes through soil that's rich in limestone or crushed limestone, or water sits on limestone, then it picks up some of the calcium and it'll pick up some of the magnesium, and the water therefore becomes hard water. Okay? And so that's water simply with significant quantities of dissolved calcium and magnesium. We'll talk in a minute about how that water appears as different, but one of the ways it appears is as taste. The water actually tastes different. Another way which is different is how it reacts with soap. Does anyone know how this water reacts with soap? If you have really hard water and you put soap in the water or detergent in the water, what do you think might happen? In the back?
It forms more precipitate.
Excellent, you're right. These things can be really insoluble. If you add a lot of detergent to hard water, the detergent will form a precipitate with your calcium and magnesium and not be available for the foaming wetting agent that the soap usually is. So people from places with lots of hard water, lots of dissolved calcium, often put more soap into their laundry than people from places with soft water. Yes, in the back?
Does it say that on the box?
No, it doesn't say it on the box.
You just kind of know it.
You just know from long habit of how much water you have to, how much soap you have to put into your laundry. So there's two types of hardness. There's permanent water hardness and temporary water hardness. So permanent water hardness is a result of So permanent water hardness is when we have the calcium and dissolved magnesium, but we don't have bicarbonate in as the anion.
Did you get the extra notes?
Oh, yeah. Yeah, I put it down.
Which makes sense. It makes sense that it's less than 2. Because if it was 200 and 200, I would end up exactly in 2. But I have slightly more of the lower concentration, so my result is shifted to this side where my larger volume is. It will always shift to the side of the always. Always.
Alright, so we're calling it permanent water hardness when we have the dissolved minerals, the calcium and magnesium, but we don't have bicarbonate present. And bicarbonate is HCO3-. Another word for bicarbonate is, call it by its polyatomic ions present. Hydrogen carbonate. That's in fact the right name for it. Bicarbonate is an old name, but like so much of chemistry, we still use the old or trivial names instead of moving to the modern names. So it's called bicarbonate. You've heard of sodium bicarbonate. We use that in baking. So this is bicarbonate. All right. Yet a better name for it is hydrogen carbonate.
How does this, how does it become present? Where does it come from?
Well, notice you can't just have calcium and magnesium ions in the water, can you? You have to have, you can't just have cations in the water, you also have to have anions. So the question really becomes is, what's the anion that's with the calcium or magnesium? Right? That's also dissolved in the water. If that anion is not bicarbonate, we call that permanent hardness. And you see why? Because we can actually quickly remove something we call temporary hardness by playing a little chemical trick. Okay? So for temporary hardness, the water also contains bicarbonate, and then we can remove the hardness. So temporary. So for temporary hardness, it contains bicarbonate. All right? So, why is this significant? Well, if we heat bicarbonate, we can actually produce, we can induce a chemical reaction. Obviously, if it requires heat, then the reaction must be endothermic. Excellent. If the reaction requires heat to go forward, then it's an endothermic reaction. So we can do an endothermic reaction encouraging the bicarbonate to decompose into carbonate. When the carbonate is present, it'll precipitate with the calcium or magnesium ions, thereby removing the hardness from the water.
You just heat it up.
There you go. Similar question. 55 mil and 75
All right,
mil.
so temporary contains bicarbonate. In this case, the hardness of the water
Bless you.
Thank you.
and the reason we call it temporary is that we're able to remove the water hardness simply by heating the water, and that's what makes it temporary. Okay? So there's an equation. We're going to look at an equation in a second, and it'll show us how, just by heating the water, we can actually cause the calcium to precipitate in the form of the calcium carbonate, and thereby remove it. The same thing applies to magnesium. We can use any of the two cations we want. So, in fact, we're going to use calcium. So we have calcium 2 plus, and it's dissolved. So it's dissolved, so it's separated out into its ions. It's going to take how many bicarbonates to balance the charge on that calcium? It's going to take 2 bicarbonates to balance that charge on the calcium. Yes?
What type of equation are you writing?
I'm writing an equation that's going to show how we can actually remove the bicarbonate from the solution. When bicarbonate is heated, it decomposes, undergoes a decomposition reaction, and one of the products of that decomposition is carbon dioxide gas. Yes?
So you know those like vitamin pills that you put in your like drinks and it makes a fizzy thing?
Okay, it's not a vitamin pill, but it is a pill you can put into your drinks, and it does make it fizzy.
No. It's like some of those. Is it kind of like hardening the water as well?
Oh yes, does it release ions? Yes. Now we had someone do that for our their project on chemical reactions. I don't know if any of the one is present from that project group here.
Was it the photosynthesis?
Hi. So over on the side, did you have a project that involved
Yeah.
fizzy thing? What did you add to the water?
Sodium bicarbonate?
It was sodium bicarbonate. So it produced bicarbonate. So it was a similar reaction because the sodium bicarbonate did dissolve into the solution, and then you got effervescence, which is when gas is released from the solution. So it was a bicarbonate, it did release a gas. It turns out, yes, it is endothermic. Now we know. Okay, good. Other thing that we're going to get out of this is water. It'll be in the liquid form, because we're carrying out this not too far from room temperature. And our remaining product is calcium carbonate. And calcium carbonate is insoluble, so we get a precipitate of calcium carbonate. So what's happening? Well, if this is a precipitate, and the calcium is precipitating with the carbonate, we've essentially removed the hardness from the water. So, water, where heating it will allow the bicarbonate to precipitate as calcium carbonate, is called temporary water hardness because it's so easy to remove. If you have water that's temporarily hard, you might notice something if you use the water, say, to make tea. Or a similar process. What might you notice? Say you have a kettle and you live in an area with temporary water hardness and you use that kettle repeatedly to make tea. Over on the side?
It would be like, it would be something behind it.
It would leave a residue. Okay, a scale. And that residue would be calcium carbonate, probably a hydrated form. It probably will make a nice crystal. It'll be hydrated, so the amount of water condensed in the structure will vary, and that's why it'll be a scale rather than a crystal. That's usually what happens when you get a precipitate and it doesn't look so nice. It's because you've got some water in there as well, so you'll have different types of hydrates in there. And so this is a real problem where you have hard water, and it's one of the negative effects, and we call it negative, of having hard water, is the scale will form inside your pipes if the water's hot, or inside your kettles, and every so often, you know, you look at the kettle and you say, oh, this kettle looks awful, there's all this scale at the bottom. Is the scale dangerous? No, it's not. It's a precipitate, it's not biologically active, it's not dangerous at all, it's just unsightly. I've even seen it form in the bottom of teacups, you know, that you use repeatedly. You get a scale on the inside of pipes. Which brings me to a really interesting story. Lead pipes were commonly used to carry water before people understood that lead was very dangerous. But in some areas where the water was extremely extremely hard, the lead pipes were not dangerous at all. In fact, I attended a school for a few years, as a faculty of education back east, where the pipes were lead, but absolutely nobody worried about it. Lead is dangerous. If you pass water through lead pipes, the water picks up some lead, and so it's dangerous to drink because lead is toxic. But these pipes, even though they were made of lead, were absolutely safe. Why? And the building had been around for a long time. Yes?
Precipitate formed on the surface of the inside of the pipes.
That's right, that's right. So the faculty of education that I attended, the pipes were lead, but over the years, because it had been around for about 100 years, there was a scale built up on the inside of the pipe, and it's such a good scale, such a thick, impenetrable scale that the water doesn't actually contact the pipes anymore. So in that way, the pipes became safe. Okay? So it's kind of interesting how these two chemical things can kind of like cancel each other out. So this is a real problem. If you have boilers, for example, in many apartments, there's a large boiler and they boil water, or they heat the water to send throughout the building. Well, if the water's hard and you heat it and it's temporary hardness, what will develop inside the boiler? Scale. And that can influence your boiler because it's taking up space inside your boiler. And if it flakes off, people get these unpleasant little flakes, this sort of white crusty material coming through, and it can clog the pipes. It's a real problem. Every so often in areas with extremely hard water, the pipes have to be replaced because the scale builds up on the inside, reducing the volume of water that can flow. Okay? So it can be a real problem. And the real problem here, of course, is that this stuff is all going to cost money to replace. So hard water can be very, very expensive. I've seen teapots with scale on the inside. They work fine, but just this flaky scale on the inside. If it breaks off and comes into your tea, it's unpleasant. It doesn't hurt the tea, but you don't like it, so you want to descale your pots or replace your pots every so often. If you have an industrial boiler or industrial piping and the scale goes up on the inside, it reduces your water flow, and that can really make it a real costly thing to replace your pipes every so often. Okay, so hard water can be really, really troubling in terms of expense. Okay, so that's one of the reasons why we don't like hard water. Okay, can hard water actually have any beneficial effects? Speak up, please.
If you are lacking in such a
That's right. It's actually a source of the minerals, calcium and magnesium, which are minerals that we need. So hard water is actually healthy for you, right? Because you're getting calcium and magnesium from your water, and those are minerals that we all need. So in many cases, you're weighing different things. It's actually healthier to drink hard water, full of minerals, really good for you, versus the economic cost of hard water. Now, earlier I was talking about laundry and how you have to add additional soap to clean your clothes if you have hard water. Is there any effects you think that might have over time?
More consumption of.
you spend more money by more soap.
Yes, you spend way more money on detergent because you're adding, half a cup just to precipitate the ions. What else? Yes?
Our clothes can like a lot more use a lot more soap.
You're actually the opposite. Your clothes actually start to get, they start to yellow. So there's a place back east where people go away to university and the water's extremely hard. And they say you have the white shirt or white t-shirt, you wash it a few times while you're away, you come back home to hang out with the folks and you're wearing what you think is your white shirt and it looks really yellow now that you come back home. Well, what's happened is the soap scum has deposited itself in the shirt over time. The precipitate from the soap and the calcium that builds up in your fabric, and your fabrics actually start to yellow. Okay? There's a thing called laundry bluing. It's like a blue substance. And you've heard of that. Some of you may have heard of that. It's an old-fashioned thing, but some places they still use it. You put that in the water, and the bluing cancels the yellow from the yellowing, and it can help your clothes appear white. So the hard water is really interesting. It's not just the fact that calcium and magnesium there are knock-on effects of hard water. Okay, so what do we need to remember from this equation? You need to remember that if you have temporarily hard water, you can precipitate the hardness as the carbonate. You could just substitute in magnesium here for the calcium. Doesn't change the equation because magnesium is 2+, just like calcium is 2+. So you can precipitate the magnesium this way. There tends to be more calcium because rocks, remember, are calcium carbonate, limestone. So we use calcium as our example. The water will release carbon dioxide gas. The rest you won't even notice this water. It just adds to the general solution, and you get a precipitate or a scale. So the word for that general precipitate is scale. It looks scaly. It's this nondescript white, off-white substance that forms bottom of boilers, inside pipes, in your clothes, in your tea kettles, etc., all from having hard water.
Mr. Blumman,
Yes?
I don't know, CaCO3 kind of like calcium bicarbonate, kind of looks like
Pardon?
Tums.
Speak up, please.
Tums. Is it Tums?
Tums, but we were just, Tums is well, you can probably look this up. It does have a lot of calcium and magnesium in it. I don't know that it is
It's like some carbonate.
it might be a carbonate. Carbonate is just such a common form.
Tums.
All right. What other ways are there of removing water hardness? Well, we can do other precipitation reactions. In fact, there's an ion in your chart that forms a precipitate with just about everything. And it's often used in the last stages of water purification. Because if there's any metal ions in there, in particular we're worried about heavy metal ions, and to some extent iron. A little bit of iron is good for you, a lot of iron is really bad for you. What ion is that? So take a look at your ion solubility charts, and take a look and see if you can find an ion in there that tends to precipitate just about everything. Yes? Phosphate. So in the last stage of many water purification processes, they add phosphate. And what phosphate will do is it will precipitate any ion that's left in solution. This can be a good way of actually purifying your water and making sure it's not toxic with heavy metals. This phosphate will precipitate. Okay? So what other ways of removing water hardness? Precipitation reactions. Okay? Precipitation reactions. Other ways of removing water hardness? Washing soda. And this is something that I do as well too, even though I'm in a place now where there's soft water. You can make your water even softer if you're going to wash by adding a little washing soda or borax to your laundry. And what that does is it precipitates the metal ions so that you get the full effect of your detergent. So washing soda is sodium carbonate, and it's present usually as a hydrate, a decahydrate.
So to review all the whole questions, I'll give you some review questions.
And something else I use is borax.
We do not have another block.
Borax is a compound that's just literally dug out of the ground and put into boxes and sold in grocery stores. And you add that to your detergent, to your dishwasher. Helps precipitate metal ions, makes your detergent or your soap go further, and provides a cleaning action of its own. So both of these things can be added to help remove hardness from water. Something else that we do to remove water is we use an ion exchange column or ion exchange gel. And so there are many different types of ion exchange that occur. We can say it's an ion exchange resin we're using, an ion exchange gel we're using, an ion exchange column. All of these different ways that we refer to ion exchange. What ion exchange is just what it sounds like. You encourage the swapping of ions. So you're going to remove the positively charged ions from the water that you're interested in removing, like the calcium or magnesium, and the iron, but you have to replace it with something else that's positively charged. Okay? So an ion exchange resin, there's an anion. So you have an anion, but the anion is attached to either beads or to some sort of surface, so it's not free to move in the solution. So if I could draw a little diagram of this, you have a surface or you have a bead, and attached to the bead will be some anion. So they're either attached to the bead, you've got the anion, but the anion's physically, like chemically bonded to the bead, or it's bonded to the surface, or it's inside the gel, but whatever it is, it's not free to move. Next to this ion will be some positive charge, obviously, you can't have separate ions, and that positive charge will be just associated with the anion. So in this case, I'm using sodium, and I'm saying that the sodium is going to be attached to the anion. So the anion is not free to move. It's a part of the structure of the bead or the resin. And attached to that is the sodium. And this is all sort of in some fluid. So it's all in the fluid, all inside here. It's going to be your water. It's in your fluid.
Are they all carbonate?
So we have an anion attached to the bead, and then balancing the charge on the anion close by associated will be a cation. Okay, so you have anions attached to the bead or attached to the resin. Somehow they're attached, and then associated with them are some cations. And these are often organic. That's why you get them attached. You make a bead, and then you have these organic groups that are negatively charged on the outside. Carboxyl groups or whatever. They're all negatively charged, and they're on the outside. And then attached to those are sodium ions, usually sodium ions. Why sodium? Because it's soluble, and it'll move for acid reason. Okay. All right. So what happens next? Well, what happens next is you take your hard water and you pour it into this exchange gel or this exchange column, and the positive ions in the hard water travel down through the resin. So I'm going to use a different color now. So we have the positive ions, in this case calcium, traveling down. Well, the calcium is going to have an attraction for the anion. And the calcium will bind to the anion, but that will release the sodium. Right? So what happens is, after you've put the calcium through, you have the anion still, but now the calcium, and we'll just put one calcium here, because I made the anion single valence. I should have made it double valence, but I'll make them single valence. And so what happens is, the calcium here is now associated with the anion, and that has released the sodium. Hence the name. It is called ion exchange, because you've changed the ion, you've exchanged the calcium ion for a sodium ion. Right? So you've ended up exchanging ions. You remove the calcium from the water, but the downside is you've also added sodium to the water, which is going to be healthier for you.
Calcium.
Calcium is healthier for you, right? Unless there's something really wrong with your metabolism, like there's only a handful of people in the world that say have problems with calcium metabolism. This calcium is way healthier than the sodium. Sodium, in fact, is... It is? Yeah, it's bad for you. It's unhealthy. Too much salt in your diet causes hypertension, and you're at risk of cardiovascular disease. So by softening the water, you've removed calcium, maybe saved yourself some money, certainly use less detergent. It's nicer to drink if you don't like the taste of hard water. But as a result, you've added in sodium and you've put your health at risk. So this ion exchange resin is not particularly a good idea because for most of them you're adding a new ion in, and that ion is sodium. Sodium is bad for you. So this has negative consequences to health. Yes? No, because the question is, does our water here have a lot of sodium in it? No, because our water is naturally soft, right? It's not soft because it's gone through some ion exchange resin in the sky. It's soft because it's fallen from the sky and fallen mostly on igneous rock, and then gone through not very much soil, and if the soil is primarily of igneous origin, it's not going to have a lot of the carbonates in it. It's going to have silicates instead of carbonates. And as a result, the water is going to be soft naturally. So naturally soft water is not a problem. It's this water that's been made soft that's a problem. Now, I did say only a handful of people have calcium and magnesium metabolism problems. There is one thing that is actually a little bit more common, and it's a little bit of a problem, and it's not just a handful of people. Kidney stones. Right? So one thing that drinking hard water can put you at risk for is kidney stones. They are not life-threatening. They are, however, very, very painful. Because the stone is an accretion. It's actually a, well, you know what it is. What do you think a kidney stone is? Yes, well, where do you think what's come from? The excess calcium undergoing a precipitation reaction and actually crystallizing in your kidney. And the difficulty is it's a hard object because it's a stone-like object, not a real stone, but it's just hard. And of course it passes through these thin tubes, the ureter and then the urethra, on its way out of the body, and those tubes are delicate, they're narrow, and if it hits any protuberance or any yeah, Superman is squirming already. If it hits anything on its way out of the body, it can be excruciatingly painful. Excruciating, debilitating, excruciating pain. And if you think of your urethra, of how delicate that is, yes, it's right up there with childbirth.
Oh, not all the way up there.
I've seen people incapacitated for days with this thing. It is incredibly painful. The good news is that now they can use ultrasound to break up the stone into smaller pieces that hopefully it'll be easier to pass. So there is a little bit of a treatment. Until recently, the last person I worked with a man who had this, and he was basically incapacitated for about a week, just on painkillers, waiting for this thing to work its way through his system. Yes?
Does it, okay, do you like, okay, which, like one or two, like which one would come up?
One. Wouldn't hurt if it was number two. It's the size of, it's a millimeter or two across, but they are hard, and that tube is only made to carry liquids.
And can it like tear? It can tear through.
It hits things, and it's really rough on the inside. It's very, very painful. Okay. All right. So that's our basic lesson on water hardness. You can, you'll read sections of the textbook to,
It's like one of the ones that don't stretch out.
oh, just perfect timing. You're going to read sections of the textbook to reinforce your understanding. The main equation I gave you was the one I put on the board earlier, where it showed how the bicarbonate, in the presence of heat, will dissociate, release the carbon dioxide gas, and precipitate the calcium. That's the big equation that you have to be able to recognize. The rest of this is really interesting. You just have to be aware of that there are other ways of removing water hardness, including precipitation reactions with washing soda, carbonate, or borax, or ion exchange. And you should be a little bit aware, just in general, of the sort of positive effects or benefits of hard water, and the negative, effects or benefits of hard water, soft water. So you understand that there's a health implication to hard water. It's actually good for your heart to have hard water because the calcium magnesium improves muscle function, and your heart's a muscle. It's bad for your heart to have soft water, particularly if the waters come from an ion exchange gel, because it's going to be full of sodium, and sodium is just bad for you in terms of hypertension and cardiovascular disease. So hard water can be very healthy, with the possible exception of it encourages the formation of kidney stones. Hard water is expensive because scale can build up in the inside of industrial apparatuses, pipes, boilers, etc. Hard water is unsightly because it can cause yellowing of clothes, and it can cause scale to form in teacups or inside tea kettles, so it's unsightly even though it is not dangerous. And there are a few circumstances where the scale can actually provide a direct benefit if you're using pipes, for example, that are made of lead. Iron is less of a problem. Small amounts of iron, of course, are also good for you. You need them in your diet. Some people, myself included, make sure that he always uses iron cookware. Because as you use iron cookware, and even like the little scraping of the pot, it actually adds iron to your food. So it's actually a good source of iron to use an iron cook pot. Cast iron is even better. Stainless steel works too, but cast iron is even better. However, too much iron can be dangerous. I remember once I was crossing the border from Ontario to Manitoba, and there's this little rest stop there, a little, get your brochures about, beautiful Manitoba or whatever. And it's a rest stop, then they had a well, you could go get some water. And there was a sign on the well. And the well said, this well has X number of parts per million iron. Not a problem for most people, but if you're pregnant or if you have certain diseases, and they named the diseases, then you shouldn't have water from this well because the iron concentration is so high. Right? And then I made a complete fool of myself. I was like, really? So my friend, my cousin actually went inside to speak to the woman at the tourist information desk and got us maps and stuff. This was a while ago. And I went and filled up our jugs with water, and I'm coming back. I'm coming back to the car, and I've got the jugs, and it's iron-heavy water, right? 'cause it's not, but of course it's parts per million iron, right? It's not, so I'm like, oh wow, these drugs are really heavy. Wow, because there's so much iron in them. And I put them in the car, and I'm having a good time, and I'm laughing, thinking it's really funny. And my cousin sits back in the car, and he says, we saw you were approaching the car with your heavy drugs. Did you think to check your fly? And yeah, so I made a great impression. So, and that's my silly iron story. Okay, so that's it. Your homework is to look on page 3, pages 102.